Hey everyone, and welcome to this explainer. Okay, we're gonna dive right into this today. If you just take a second and look around you right now, literally everything you see, from the screen sitting in front of you to the exact way you're resting in your chair, it's all being secretly governed by this invisible operating system. You know, we so often think of physics as just, well, a bunch of really complex equations scrawled on a dusty chalkboard. But in reality, it is the fundamental code of the universe. So today, we are decoding that exact source material to figure out the hidden rules that dictate how our entire world moves, crashes, falls, and perfectly balances.
So here is our roadmap for today's journey. We'll be covering the language of motion, forces and Newton's laws, the physics of falling, momentum in car crashes, and finally, balance and turning effects.
All right, let's kick things right off with Section 1, the language of motion. Because obviously, before we can understand how the universe moves, we need to make sure we're actually speaking the right vocabulary. Now, there is a super crucial difference between the two main types of physical quantities out there, scalars and vectors. Scalars are basically just simple numbers. They only have a magnitude, which is just a fancy word for size. Think of speed, distance, or mass. A car is going 50 miles per hour, and that's it. Story over. But vectors? Vectors demand a lot more information. They have magnitude, sure, but they also have a very specific direction. So velocity isn't just 50 miles per hour. It's 50 miles per hour heading straight north. Displacement isn't just the distance you traveled. It's the directed distance from your exact start to your exact endpoint. Heck, even your weight is a vector. Why? Because gravity is constantly pulling it in a very specific direction downwards. And that brings us to one of the absolutely most important vectors out there, acceleration. The source material defines this simply as the change in velocity per unit time. Now, usually when we hear acceleration, we just think about slamming on the gas pedal and speeding up, right? But remember what we just talked about. Velocity includes direction. So if a car's speed actually decreases, which we normally call deceleration, or, get this, even if the car stays at the exact same speed but simply turns a corner, it is officially experiencing a change in velocity, which means, scientifically speaking, it is accelerating. Crazy, right?
So, what actually causes all these constant changes in velocity? Well, let's move right along to Section 2, Forces and Newton's Laws, to figure that out. Let's quickly break down the ultimate rulebook here, Newton's 3 laws of motion. Law 1 basically tells us that if the forces acting on an object are perfectly balanced, that object is either going to just sit completely still, or if it's already moving, it will just keep moving at the exact same constant velocity. Law 2 is where things get interesting, because it kicks in when things get unbalanced. An unbalanced or resultant force literally forces an object to accelerate. This is captured in that famously simple equation F equals ma, or force equals mass times acceleration. Basically, a bigger force means a bigger acceleration, but a heavier mass means a smaller acceleration. And finally, we have Law 3. Forces always act in equal and opposite pairs on different objects. These 3 rules dictate absolutely everything around us, from a cardboard box sitting quietly on a table to a massive rocket launching into outer space.
Now, what is truly mind-blowing is how Law 3 actually plays out in our everyday lives. When Object A exerts a force on Object B, then Object B exerts an equal and opposite force on Object A. This is the core ethos of physical interaction. Think about something as simple as just walking down the street. You probably think you're pushing yourself forward, right? But physically, you are actually pushing the ground backward with your feet. That is the action force. The ground then exerts an equal and completely opposite reaction force forward right onto your feet, and that reaction is what actually propels you down the sidewalk.
So let's apply all these forces to a really high-stakes scenario, trying to stop a moving car. At exactly 0.0 seconds, a driver spots a hazard in the road. But here's the thing, the car doesn't start slowing down quite yet. It takes a split second for the human brain to process that danger and physically move to press the pedal. We call this the thinking distance, and it's all happening while the car is still flying forward at its original speed. Then the brakes finally engage, creating friction to actually decelerate the vehicle. This part is the braking distance. The crucial takeaway here is that factors like higher vehicle speed or a really heavy car mass will drastically increase that braking distance. Meanwhile, if a driver is older, fatigued, or maybe intoxicated, they'll have a much longer reaction time, which dangerously extends that initial thinking distance.
All right, from the roads, let's look up to the sky for Section 3, the physics of falling. Let's see what happens when gravity takes complete control.
10, or to be exact, 10 meters per second squared.
You see, if you take away all air resistance and drop objects in a pure vacuum, gravity is acting entirely alone. This is what we call true free fall. In a vacuum, gravity will accelerate all falling objects, whether it is a heavy bowling ball or a super light feather, at approximately 10 meters per second squared. That means every single second they fall, their velocity increases by exactly 10 meters per second. Without air getting in the way to mess things up, mass totally doesn't matter, they will hit the ground at the exact same time.
But obviously, we don't live in a vacuum, do we? We live in an atmosphere. So let's see how this actually plays out in the real world with the story of a skydiver. The moment they first jump out of the plane, their speed is 0, so there's practically no air resistance yet. Gravity pulls them down and they accelerate super rapidly. But as they fall faster and faster, fluid friction, or what we call drag, starts to build up, pushing upwards against them. Eventually, that upward drag force perfectly equals their downward weight. The forces are now totally balanced. Newton's first law suddenly kicks back in, their acceleration hits 0, and they just fall at a constant, maximum speed. We call this their terminal velocity. Now, when they finally pull the parachute cord, that massive new surface area creates a huge surge of upward drag, creating a very unbalanced upward resultant force. This causes rapid deceleration until a brand new, much slower, and much safer terminal velocity is reached.
Now that we've covered the physics of falling, let's take a look at really sudden stops. Welcome to Section 4, Momentum and Car Crashes.
Okay, here's a question for you to chew on. Why on earth do modern cars crumple on impact? Back in the day, people totally thought heavier, incredibly rigid cars were way safer. But today, engineering intentionally designs the entire front end of your car to crush like an accordion in a crash. I mean, why would we want our really expensive vehicles to just destroy themselves so easily? Well, the answer to that actually lies entirely in this one concept: momentum. Momentum is officially defined as the product of an object's mass and its velocity. But you can really just think of it as a measure of exactly how hard it is to stop something that's already moving. A really heavy truck moving incredibly fast, that has massive momentum. And a fundamental rule of our universe is the conservation of momentum. This means that in any closed system, like two cars colliding into each other, the total momentum before the crash must exactly equal the total momentum after the crash. The momentum doesn't just magically disappear, it just transfers.
And here is the absolute golden rule when it comes to crash survival. More time equals less force. The source material outlines this really clearly. It shows that force actually equals the change in momentum divided by the time it takes for that change to happen. So, if a car crashes into a solid brick wall and stops dead in just 0.02 seconds, the change in momentum is incredibly fast. That results in a massive, totally devastating force on the human body. But if you can just slightly increase the time it takes for that momentum to eventually reach 0, the destructive force drops dramatically.
And honestly, this concept explains exactly why modern cars are built the way they are. Those crumple zones we just talked about, they are explicitly designed to crush, basically absorbing the energy and artificially extending the total collision time. Airbags do the exact same thing. Instead of your head hitting a rock-hard dashboard instantly, the airbag slows your head down over a slightly longer period of time. Even your seatbelts are actually designed to stretch just a little bit upon impact. Every single millisecond of extra time that these features buy you means considerably less force acting on your body, preventing severe injury. It's quite literally pure physics, saving your life. All right, let's step away from the intense world of crashes and slow things down just a bit for our final section today, Section 5, Balance and Turning Effects.
We've been talking a whole lot about forces pushing things in straight lines, but as we all know, forces also make things spin. In physics, this is called a moment. A moment is simply the turning effect of a force around a fixed pivot point. You can calculate it pretty easily by just multiplying the force you apply by the perpendicular distance from that pivot. So the further away you apply your force from the pivot, the much larger the turning effect you ultimately create.
And what's cool is we instinctively use moments every single day to essentially multiply our own strength, without even thinking about it. Think about trying to loosen a tight nut with a spanner. You always grab the handle as far from the nut as you possibly can to maximize that distance, thereby maximizing your moment of force. When you're using a pair of scissors, you apply force to the handles, which then pivots around that tiny central screw to bring the blades together with concentrated cutting power. Even a classic wheelbarrow works directly on this principle. Lifting up those really long handles allows you to pivot incredibly heavy loads straight over the front wheel, using a surprisingly tiny amount of applied force.
So the crucial point here is understanding exactly when things actually stop turning, and this is all governed by what we call the principle of moments. It basically dictates that for an object to be perfectly balanced, or to use the scientific term, in equilibrium, the total clockwise moments must exactly equal the total anti-clockwise moments acting around that pivot. If they don't match up, well then there's a resultant moment, and the object is going to rotate. But if they do match perfectly, they just cancel each other out entirely, and the object stays completely, perfectly still.
Now, this whole idea of perfect balance ties directly into something called the center of gravity. That's basically the single point where an object's entire weight appears to act. So, take a standard 100-centimeter wooden ruler. Its center of gravity sits dead center, right at the 50-centimeter mark. If you were to place a pivot point exactly under that 50 mark, the ruler is going to balance flawlessly because the weight is distributed completely equally on both sides, which creates absolute zero rotational forces.
Which actually brings us to the end of our explainer today. But I want to leave you with something to really think about. As you sit there right now, seemingly motionless, gravity is constantly pulling you down, the chair beneath you is providing a normal force pushing you right back up, and tiny frictional forces are keeping you perfectly in place. Everything about you right now is in a state of absolute perfect equilibrium. So considering this constant, totally invisible mathematical tug of war happening all around you at this very second, are you ever truly at rest? Or are you really just the center of a perfectly balanced universe of forces? Thank you so much for exploring the fundamental code of reality with us today. Keep looking closely at the world around you, because trust me, you will start to see the physics everywhere.